مرحبا طلاب، كيفكم؟ أرجو أن يعني تفوتون للفيديوهات اللي حطيت لكم إياها مشان I can see عدد الفيو، لأنه مطلوب من عنا نحط يعني مين اللي، وانتوا حكيتوا إنه أنا تأخرت عليكم فشوفوا يعني الفيديوهات اللي حطيت لكم إياها. يلا let's start. أنا بدأت بمعنى dumping in the system، وهذا الفيجر حكيت لكم عنه، فأرجع عليه بطريقة ثانية. إنه هنا قلنا إنه نطلع الروتس of the equation، يعني of the denominator، ونشوف إنه إذا الروت real and distinct it's overdamped، إذا real and equal is critical، إذا complex it's underdamped، وإذا يطلع لي هيك sustained يعني pure oscillation معناها no damping. فإذا معناها إذا هذا اللي طلعناه واللي هو بين عليه هنا overdamped معناها زيتا greater than 1. أوكي؟ رجعت على هذا الشكل مشان أحطه in terms of zeta only، مش إنه بدي أعيد على الفيجر. أوكي؟ Here I have complex root، I have system with the oscillation as you notice. So here zeta أكبر من صفر وأقل من واحد. Now here as you see there is the midterm is missing. So here I get pure oscillatory, pure oscillation, sinusoidal output. So zeta here is equal to 0, no damping, right? And the last one is when I have two equal roots and real. This means that this response, they call it a critically damped response. Here zeta is equal to 1. Okay? Now, in this time of video, I wrote everything so that I'll save some time. Maybe later, and if I have feedback from you, I can see what would you like to write and talk, or to prepare المحاضرة قبل. A second order system can be, as we said, put as omega n square, s square plus zeta 2 zeta omega n ps times omega n square. This is equation 422. This is a very important equation, as all our work in this course, I mean ME344, we refer to this. This is a standard form of a second order system transfer function. The roots of this denominator, as we said, it will define the response. So if the roots or poles are given by like that, I'll take the denominator. This is the denominator equated to 0. Get the roots. I get minus 2 zeta omega n over 2, so it's minus 2 zeta omega n plus minus omega n, and under the square root zeta square minus 1. So it depends, as I talked in the last video, that it depends on the value of zeta, and it depends on the value of this what we call the المميز. We get the response overdamped, underdamped, critical damped, and so on. So if the response we get real, then we get real roots. If not, we get complex or critical. Now let's take a simple example, which is like that: 36 over s squared plus 4.2 s plus 36. The question is asking you to find zeta and check if the system is underdamped. So we take this coefficient, it's equal to zeta omega n equal 4.2. So zeta equal 4.2 divided by 2 omega n. Omega n is this one under the square root, so it is 36 under square root equals 6 rad per second. Then zeta equal 4.2 over 12, 2 times 6, 12. It's equal 0.35. Actually, as an information, this is a bad zeta. It's too small. So zeta is less than 1, and then system is underdamped. You remember that in the first lecture, how to find if system is underdamped, overdamped, critically damped. We have to find the roots and see if they are real, complex, or equal, or not equal. But here, it's an easy check over the damping just to find zeta in this way. That's the difference between the two methods. Same, this task problem that I'll give you example so that make the concept which I am giving you easier. So we have two systems. It's more than two systems, but I'm giving you two systems. I have this one, and he wants us to check the damping. So we take this again, this middle coefficient of the middle term, check damping, 2 zeta omega n equal to 12, zeta equal 12 over 2 zeta omega n. So zeta equal 12 over 2, and omega n is the square root of this 400, which is 20. So it is 12 by 40 equal 0.33, and omega n, as I said, is equal 20. Of course, rad over second, the omega. Okay, it's a frequency. If you want to check more, if you like, so we take the denominator, which is s squared plus 12s plus 400. We can get the roots, and the roots. So it's this is 0.3 if a system is underdamped, of course, and the roots as for underdamped must be complex. So if we analyze the denominator, we find that S1, S2 equal minus 6 plus minus J 19.079, which are complex. Okay. Now, if we take the second one, C, this one, omega n is the square root of 2 to 5, which is 15, and this is 2 zeta omega n, remember, is 30. So we say that 2 zeta omega n equal to 30, omega n equal 15, and then zeta equal 30 over 2 times omega n, so 30 over 30 equal to 1. This is a critically damped system. If you want to check, take this one and find the roots, if you like. S equal minus 30 over 2 and plus minus, this is 30 square minus 4 times 2 to 5. This is 900 and this is 900. So or this will be 0 and the roots will be minus 15, real and equal. So it's a critical system as the rule which we know for a critical system. Okay? Now let's come and to the system again. As I told you, we'll always use this system. Why we coming back to it? We're going to study the response. We're going to study the characteristic of the system. This is a major topic in this subject. So if we have again g of s equal omega n square, if you like, we could put equal omega n square over s square 2 zeta omega n s times omega n square, and it's equal to output over input, as we know. So c of s equal the transfer function, this one, times r. If we assume r equal 1 over s, which is a step, then we want, what do you want here? We want to find the response. Because r is equal step, then we get a step response, okay? So the name for the type of the response is given from the input. So if I give an ramp input, I say ramp response, okay? Now, how do you find the Laplace inverse of this and find the C of t? So this one is equal, you remember from Laplace, equal k1 over s, because I multiplied this instead of here. And so it's k1 over s plus k2s plus k3, because this is second order, s square plus 2 zeta omega n s plus omega n square. Of course, we'll come later and we solve many questions and it will be easier for you. But now I just want to tell you, if you get the roots here for the system real, then no problem. You can go and perform partial fraction expansion and find the constant, as I told you, by the quick method or any method you know. So you'll find k1, k2, k3, and then you use Laplace transform and you find the Laplace transform inverse from tables. So if you get, if the system is critically damped, overdamped, you can solve it by partial fraction. Now, if you get complex roots, like when zeta is less than 1, so you'll get root like this, which are complex. When we get complex, then to solve this, it will be more difficult. It's not impossible, but it's very long. So control box, which deals with this transfer function for control and for engineers, they found you an expression for this problem. So if you have the response with S1 that will be complex with zeta less than 1, then the response is given like that. 1 minus 1 over beta a2 minus zeta omega n phi t cosine omega n beta phi t minus phi. Okay? This is the response is given you. And if you have exam, this will be given to you. And it's in the books, and some people, they put it in the Laplace transform table. What's beta? It's 1 minus zeta square. What's phi? Is tan inverse zeta over beta actually. Okay? I hope this is clear. So if we have, I'll repeat, if we have real roots, we have no problem. We go into partial fraction, and sometimes it's given to you as partial fraction in the Laplace transform table, and you find it directly. If the roots are complex, then you use this directly. You can find what's zeta, what beta, what's omega n times b. Actually, we're going to learn that's omega n times beta is omega g, the damp frequency, and all these parameters can be found easily, right? It's much easier than if you use the method for partial fraction if the roots are complex. Of course, if we have, why we talking about underdamped response? Because it's more commonly used. When the system is underdamped, especially if if the damping is a bit little, not much, then the system, I hope it's clear because I draw it on different pencil. It's not very dark. But it's okay, I think. And it's found in the book. It's figure 413. You can find it in the book. It's not something to memorize. You will learn it by solving other examples later. So we like underdamped system. Not very much underdamped, a bit of zeta. Why? Because it will be easy on the system component. If we put too much damping on the system has to work hard to get the response. So the component will get old quicker. So they put a bit of damping, so that system will be like it will move easily. Okay. So this is a group as with different zeta here. They are all underdamped because we are interested in underdamped system. It's more general. So we consider this is the general case, and the other responses, because they are easier, overdamped, critically damped, they are easily found. This has all the characteristics we need about a second order system. So you notice that as zeta is getting smaller, this one, let's say, let me put this pen, this one, this is zeta equal 0.2, the oscillation is higher, okay? As zeta become bigger, which is here, 0.8, the oscillation is less, okay? The oscillation is less. So if you put a bit of zeta, like big zeta, not a bit of zeta, like 0.7, it will be a small oscillation, and it's nice on the system. We'll go into that later again. So we notice that from the figure as zeta decreases, the oscillation increases, okay? فالتناسب عكسي يعني. Now, underdamped response is commonly found in real life, as I told you. In design, we need some facts and figures about this response so that we can do some design. We talked about some parameter for first order system like settling time, rise time, time constant. We'll talk about this here, and extra parameters for this system. All these parameters are key parameters for this response so that we can design the system. We can choose these parameters properly. If we choose this parameter properly as rise time, settling time, as I said, peak time, percent overshoot. What's percent overshoot? The amount of this overshoot from final value. This is the final value. This is the amount, how much you go out of this final value up and then you come down. This is call it the peak and the amount of overshoot in the system. So what parameters we have? We have, first of all, we have rise time. It's like the one we give in first order system. It's the time to rise from 0.1 of the final value to the 0.9 of the final value. Okay, I'll show it to you on the figure later. The peak time is the time required to reach the first or maximum peak, Cmax and figure. I'll talk about the figure, maybe it's easier. Here it is. Here is the figure. I'll take this one away. Look at the figure. I hope it's clear. Okay, that's the peak. So the system will oscillate, and I said before that we're going to consider the underdamped system. This is an typical underdamped response. This is the final value. Okay, this is the peak time. The system go to maximum, then it goes down, oscillatory. It's a damped oscillatory system. So this time here, where is my maximum? Here I call it peak time. This one, TP, okay. Now, this time the rise time is between 0.1 of the final value. This is the final value. So 0.1 of the final value, I put it here, and 0.9 of the final value. This is the rise time, okay? Between 0.1 and 0.9. Actually, it's very hard to calculate, but we'll talk about it later. What's the settling time? We said we have this strip of 0.95 of the 0.98 of the final value, and the one above 1.02 of the final value. If the system oscillation goes into this strip and doesn't come out, when it first goes into this strip and stay in, doesn't come out, this is the settling time. So this is our settling time. Okay? So we had rise time, we had peak time, we had settling time, we have, this is the final value, this is the maximum peak value, and this is all the characteristic of the response of a system. How to calculate all this? This is our next topic, okay, to talk about it, is how to find it. Once we find these parameters, we find the key points of this response, all the good key points for the system response. If you design the system with good TP, TR, TS, percent overshoot, that's it, you can draw and write the transfer function of the system, okay?